Veterinary Neurology Journal article reviews presents Accuracy and Safety of 3D Printed Animal-Specific Drill Guides for Thoracolumbar Vertebral Column Instrumentation in Dogs, Bilateral and Unilateral Design. It was published in Veterinary Surgery in 2021. The main author has affiliations at the University of Bern and the University of Wisconsin-Madison. Please look on the Veterinary Surgery website or PubMed for more information on the articles and also the author. There is a growing interest in 3D printed guides for surgical planning to improve safety of implant placement, as highlighted here in the introduction. Technical benefits include not only the accuracy and optimization of safe drilling corridors, but also possible superior biomechanical properties of screws, reduced surgical time, and reduced morbidity. To be clinically feasible, guides need to be rapidly created, inexpensive, and safe. With any technique, however, there are limitations such as 3D design software knowledge, the requirement for clean bone preparation, and the production of debris intraoperatively. The differences in accuracy between different 3D printed drill guide designs or specific design recommendations have not been reported in veterinary medicine. In human spinal surgery, drill guides can be designed for the intent of bilateral or unilateral stabilization, whereas in veterinary surgery, those reported in the thoracolumbar spine only have bilateral designs. Because of the limited data available for unilateral instrumentation, the objective of this study was to compare the accuracy and safety of two drill guide designs for use of instrumentation of the thoracolumbar vertebral column of dogs. The group hypothesized that the bilateral design would have superior accuracy compared with a unilateral design, and that both designs would be safe. To summarize the study design, a single cadaver was used and guides were made from T8 to L7. Two drill guide trajectories were created in the cranial to caudal aspects of each vertebral body, passing obliquely from a dorsal abaxial to ventral axial orientation, and then inspected in orthogonal planes to ensure no corridor breach. For bilateral drill guide design, a connector or an inverted U-shape going over the spinous process connected the drill guide to a contralateral base. Please reference the article for more details on the guide design. For the cadaveric surgical process, a standard dorsal approach was performed bilaterally with the dog in sternal position, and the drill sleeves were placed on the designated vertebra. As shown in the figure, a drill sleeve was placed in the 3D guide. Then a CT was performed following drilling. Pre- and post-operative data was compared and an average deviation was calculated. I've used the same calculation before for a study of mine where we take the square root of x2 minus x1 squared, then y2 minus y1 squared, and finally z2 minus z1 squared. And then this average is taken. But I feel what's more important than this equation looking for deviation is if there's actual cortical breach, and they also evaluated that in this study. Looking at the results, the approximate time for design of a drill guide for a single vertebra was under 20 minutes. In total, 13 unilateral and 13 bilateral guides were created. There was no difference between the two designs in angle and entry deviation. There was a decrease in exit deviation for a unilateral drill guide compared to the bilateral drill guide. When all drill guides were considered, the mean angle deviation of the trajectories was less than 3.5 degrees, and the maximum angle deviation was 9.3 degrees. The mean entry and exit point deviations were less than 1 and 2 millimeters respectively. The maximum entry or exit point deviation was 4.7 millimeters. Prior to talking about the next section, let me review the grading system on cortical breaches. This comes from the benefit and accuracy of intraoperative 3D imaging after pedicle screw placement, a prospective study in stabilizing thoracolumbar fractures. So going through the grading scheme, 1A is going to be ideal, where the screw is placed in the pedicle and vertebral body as planned. 2A is the pedicle screw goes too lateral within the vertebral body, and 3A is the pedicle screw is too far lateral in the body and the pedicle. 1B is the pedicle screw is a little bit lateral in the pedicle, but it's still a reasonable location within the vertebral body. 2B is the pedicle screw is at a reasonable location within the pedicle, but it crosses midline on the vertebral body. And then 3B is too far medial on the pedicle and is entering into the canal and also crosses midline on the vertebral body. So going back to the study, vertebral bone cortex breach was identified for 2 of 52 trajectories, so very small percentage. According to the classification system, all drilled trajectories but 2 were classified as a type 1, with 1 being a type 3A and then 1 being a type 2A. An example of cortical breach can be seen in figure C, being a 3D recon where we can view the vertebral canal and you can see the hole or the breach that has occurred. Just to get some closing thoughts, the accuracy of drill guides in the study is in line with another previously reported study. That said, the exit point deviation was significantly different between the unilateral thoracic drill guide and the bilateral, with the unilateral being more accurate. This seems reasonable as there's less entry and exit points and it could lead to a type 1 statistical error. I think overall this study shows, like most 3D printed guide studies, that additive manufacturing can create accurate 3D guides. That said, it is important to understand the limitations of 3D printed guides. Although guides can be made in 20 minutes, at least the design, it takes hours to actually print the design and then another hour, potentially longer, to perform the post-processing of the design. And then it also has to be sterilized. For me, I can have a print done, so a total turnaround in 24 hours as a very reasonable time to where it prints overnight, and then I do the post-processing the following morning. So in theory, I can perform CT on a patient one day and then be able to do the surgery the following morning or early afternoon. For a dog with a spinal fracture, we might not have this luxury, and a freehand technique is often needed. Additionally, there is a learning curve to each step of the 3D design and each software. There's not one software that can do every step of this procedure at this point. And from what I've gathered, it seems that very few people can do all of the steps, and everyone seems to have their own technique for the people who are doing the 3D prints. For me, I find it very beneficial just learning how to design the guides, as it makes one more familiar with the anatomy. So even if you never place the guides or plan on printing the guides, just creating the design, as I am here, is extremely helpful. I have also created guides for other neurosurgeons at other facilities, so if anyone ever needs guides designed and printed, please feel free to reach out to me. Again, there is a learning curve, but anyone familiar with neurosurgery can place these guides with just a little bit of coaching. So the outreach for 3D guides is huge compared to other techniques, such as neuronavigation. Let me know your thoughts in the comments below, and I look forward to the next article review. If you have an article that you would like me to review, or if you would like to be part of the review article process, please reach out to me and let me know, and I would love to have you on board.